Now we address the question of what would be the uncertainty in a rectangle, given the length and width as measured, and the uncertainty in measuring of the length and the width. Okay, well, the area of the rectangle is length times width, x times y. And without using any calculus, we can say that, okay, x really means x plus or minus dx. Y really means y plus or minus dy. Dx and dy, again, being the uncertainties in measuring x and y. So that multiplying these out, we get xy, and then we get plus or minus dx times y, which is here, plus or minus x times dy, which is here, and then plus a dx dy. Now the dx dy, assuming the dx and dy, the uncertainties are much smaller than the measurements, the dx dy is going to be much smaller than the measurement times dy, since dx is much less than dx, and y dx is going to be much less than dx dy because y is much bigger than y. So we're going to assume this is 0. As we saw last time, this can lead to a little bit of inexactness, but as long as we understand that, this is a completely valid and useful procedure. So what we have here is the calculated area and the uncertainty. The uncertainty being y dx plus or minus x dy. Now, we want to calculate what's called a differential. You should know about differentials from first year calculus. And as we discussed in class, your calculus book, almost every calculus book, any calculus book I've ever seen, has a section on differentials. It's one of the most important topics in calculus, one of the most important applications, and one of the typical problems in an application of the differential is calculation of uncertainties and errors. Now, whether your instructor chose to assign the problems that are related to that topic depends on your instructor's style of the course and decisions about content. As I've said many times, nobody ever covers everything. Everybody makes their own decisions about content. So it doesn't mean you had an inferior course, but to the question of where can we find this information, you can find it in your calculus book. Now, in calculating the differential of xy, well, a differential is very closely related to a derivative. The product rule applies to differentials as well as to derivatives. So that the differential of xy is the differential of x multiplied by y plus the differential plus x times the differential of y, however you want to say that. So the differential of xy is the differential of x times y plus the differential of y times x, and the differential of x is just dx, differential of y is just dy. So their differential of xy is dx times y plus x times dy. Now we could get more rigorous with this. That's done in multivariable calculus. It's not one of the most difficult concepts in multivariable calculus. But multivariable calculus, although many people are taking it concurrent with this course, or vector calculus, is not a requirement for this course. We're not going to go into that much detail. We're going into a lot of detail on uncertainties to start with. But that's going to be related to the way we interpret our labs. And so it's quite important. Okay, now, let's say that x is 12.0, and I mentioned in class that it's very unlikely that all your measurements will end up with 0.0, but for the purpose of illustration, I've chosen to make it so. So you've measured it, and it's 12.0, not 12.1, not 11.9, it's 12.0, but you have a plus or minus of 0.03 in that measurement. That is an uncertainty of 0.03. Notice I've also suppressed the limits here, not the limits, the units. Haven't mentioned what the units are. We used them before. You understand that you would use them here if you had whatever set of units you have. Okay, so x is 12 plus or minus 0.03, y is 6 plus or minus 0.02. Now I'll mention right now that the percent error, 0.03 out of 12, is not the same as the percent error that you get from 0.02 out of 6. So that x and y will have different percent errors. That's not an unusual circumstance, although when you're measuring rectangles with a single measuring instrument, you might tend to have the same uncertainty. You're not going to have the same percent uncertainty. If the uncertainty was 0.03 both times, 6 being less than 12, you would have a higher percent uncertainty in y, even if you did have the same literal uncertainty in the measurement. Now I'll come back to the notes I have up here a little bit later. They're for clarification. They're not part of the train of thought here. Our dA, which is our differential of xy, is dx times y plus dy times x. If we plug the dx and the dy and the x and the y in here, we get dA equals this expression. I'm not going to read it to you. It comes out 0.42. So the area is, our area is 12.0 times 6.0 length times width plus or minus the uncertainty, which is 0.42, and that comes out 72 plus or minus 0.42. The percent uncertainty, therefore, is 0.42 over 72, which is approximately 0.6%. Now, this is a true statement. In other words, 0.42 over 72 is 0.006, but 0.006 is 0.6% because 0.6% is 0.6 per 100. Dividing 0.6 by 100, we get 0.006. So there's nothing that's not rigorously correct about that equality there, or that approximate equality. So our percent uncertainty is about 0.6%. Let's compare that with the uncertainty in x and the uncertainty in y. The uncertainty in x is 0.03 over 12, which is 0.25%. Uncertainty in y is 0.02 over 6, which is 0.33%. When we add 0.25% and 0.33%, we get 0.58%, which is pretty much the same as 0.6%. And as a matter of fact, if we divide this accurately, we get something a little less than 0.6%. And I think that to two significant figures, this will be 0.58% to match this. Remember that the dx squared term can give you some slight discrepancy between these, but since the percent error is so low, these two should come out to two significant figures to be identical. My note at the top here, if you want more information, and as I was talking about this, people did ask where you would go for more information, you can look at differentials and propagation of errors, either separately or together. You can search that on the internet and you're going to get some good information. Naturally, you want to use a little bit of judgment in the source that you rely on, but basically any source that explains this in a way that's compatible with the way it's been done here is going to be a reliable source. I'll mention down here I said differential of x was the same as dx. That looks like it ought to be the same. This is a justification for that. The differential of x squared is 2x dx because 2x is the derivative of x squared. The differential of x is 1 dx because the derivative of x is 1. And that's just equal to dx. And that's your justification for the fact that the differential of x can be written dx. Similarly for the differential of y.